Okay, so let's get started. The title for this course is Design and Analysis of Algorithms. So for this video and the next couple of videos, we're going to look at analyzing algorithms. So what is an algorithm really? This is just a step-by-step procedure in order to perform some task in a finite amount of time. So we have some input, which is provided to our algorithm. So in the case of sorting integers, this could just be a list of unordered integers. Our algorithm performs some steps and then produces an output. So sorted integers, for example. The two main things that we're concerned with when analyzing an algorithm is it correct? Does it actually work and produce the output that we expect? And how efficient is it? And efficiency is in terms of how many resources it needs, how fast is it? So this is both time complexity and space complexity, how much memory it's using. So for time, we can look at the running time of an algorithm and as it grows with the input size. So for example, sorting just maybe 5 elements would be an easier, faster task than sorting 5 million elements. So there's 3 cases that we can look at with the running time. The best case, average case, and the worst case. The best case running time isn't the ideal standard to measure against because it's not really representative about how efficient an algorithm is if you express the running time in terms of the best case. The average case is usually difficult to determine because it requires us to define a probability distribution on the set of inputs. This is usually difficult. It requires a lot more heavy math and probability. We'll see a few examples of this though. But we are going to make an algorithm with a good worst case running time the standard of success because this ensures that the algorithm performs well on every input. So we're going to analyze algorithms from the standpoint of what is the worst case running time. So how would we figure out what the running time is? We could do an experimental study. So this means that we actually write a program that implements that algorithm and then we run a series of tests to see for different inputs, for different sized inputs, how long does it take? So you could just plug in a timer to figure out how many seconds it takes for that algorithm to complete and then plot the results. But there's some downsides of taking this experimental approach. There are a few limitations to this. Mainly that you would actually have to implement the algorithm. And the entire purpose of designing and analyzing an algorithm is that we're still in the design phase. If we want to determine if an algorithm is efficient enough without implementing it yet, because if it's not efficient, then the implementation is a waste of time. So we're still in the design phase here. But also, if we did already have it implemented, any experiments that we do would be on a limited set of test inputs, and that might not actually be representative of the type of input that that algorithm would be getting. And this is also difficult to compare. So if you have person A that runs their algorithm on a supercomputer, they might have a really poor algorithm, but because it's on a supercomputer, it takes not a very long time. And another person who writes an excellent algorithm, but they execute it on computer B, which is 20 years old and takes longer. So this is tough to compare when you're not using the same hardware and software. So rather than implementing the algorithm and running empirical tests on it, instead we're going to look at a theoretical analysis. So in order to do this, we use pseudocode. This is a high-level description of the algorithm. You don't actually have to implement it at all. We'll see an example of pseudocode next. This is a mix of natural English prose and some programming details. This is enough detail so that you know how the algorithm works, what steps are required. But when we theoretically analyze an algorithm, we'll take into account all possible inputs. And we'll look at the running time of this algorithm by f of n, a function of the input size. So n is how many elements we're inputting into our algorithm. This will let us evaluate how fast an algorithm is, completely independent of the hardware or software that we're working on. So pseudocode is essential in analyzing the theoretical runtime of an algorithm. So let's see what that looks like. So again, this is a high-level description of an algorithm, more structured than English prose, but less detailed than a program. So this hides some program design issues like memory management, for example. But this is our preferred notation for describing algorithms. So you can see here we have an example algorithm, array max, which takes an array A as our input, and n is the number of elements that we have in that array. And our goal is to output the maximum element of our array. So this probably looks familiar to you. This looks a little bit like C++, a little bit like Python. It's kind of a generic mix of some of the programming languages that you've seen. So we've got, in order to find the maximum, we're essentially going to start at the beginning of the array, work all the way through the array, and keep track of whatever the current maximum is. So we have a few operations that we're doing here just to kind of illustrate what the syntax is in this pseudocode. We have a variable called current max, and we're taking the first element of our array A, so we're accessing an element in the array here, and assigning that value to the variable current max. So the arrow here works very much like a single equals would in C++. Then we have a for loop, so beginning with the next element of our array, so I is that index, and going all the way up until n-1, we're going to check to see if whatever element is stored at index I of our array, if this is larger than whatever our current maximum is, then we're going to just reassign current max to be that new larger value. And then when we're done, once we've gone through all n elements of our array, we return what that current maximum is. So again, this is pretty similar to what you've seen before with how you would write this similarly in C++ or Python. There are a few things to note. So some of the details that we have here, we have all of the main control flow statements that you would see: if, then, else, else if, while loops, repeat until loops. So repeat until, this would be the equivalent of a do while loop in C++. So a while loop will check a condition, test that condition before it starts executing. A repeat until will first execute that chunk of code, and then afterwards it will test a condition. For loops, for each loops. You'll notice from the previous example that we're using indentation instead of braces. So this is more of a Python-esque type of style. So let me go back for a moment. We have that everything inside of the if statement is indented by one tab. Everything inside of the for loop is indented, etc. When you declare a method, you specify here's the method name, and then whatever optional arguments you have. So these have names so that you can use them within your algorithm. And you specify whatever the input is and whatever the output is. So this is kind of describing what the algorithm does. When you call a method in pseudocode, either on a data structure or just calling a separate function, this is just done the same as you would, again, in C++. You can return a value or an expression, and some of the expressions we have are assignment. So this is using an arrow. This is the same as an equal sign in C++. Equality testing is just an equal sign. This is the equivalent of double equals in C++. And there are also other mathematical formatting which is allowed. So for example, you could just write directly n squared or n cubed rather than having to call like a separate function like Powell for that. Okay, so pseudocode gives us enough details on how an algorithm works so that we can evaluate how efficient it is. And in order to do that, we imagine this algorithm being executed on a random access machine model. So this just simplifies the idea of what a computer is and what it's capable of in order to make our analysis easier. So this just views a computer as a CPU, and that CPU has an unbounded bank of memory cells. Each one can hold some arbitrary number or character, and importantly, we can access these memory cells in unit time. So the term random access here refers to the ability to access any one of these memory cells with one primitive operation. So primitive operation, this is just a basic operation which takes unit time. So our goal with this is when we evaluate the theoretical runtime of an algorithm, we're going to count up how many primitive operations does it require. These are those basic computations performed by an algorithm. So if we have the pseudocode, we can identify what those primitive operations are in it. But importantly, this is independent of programming language. And these primitive operations are assumed to take constant time in our RAM model. So this includes things like evaluating an expression. So if we evaluate 5 plus 3, this is one primitive operation. Assigning a value to a variable. So if we assign the value of 5 to the variable x, that's one primitive operation. Anytime you index into an array, so accessing the first or the third or the 10th element of an array, that's one primitive operation. When you, just the act of calling a method, not actually executing everything which is inside that method, but just the act of calling it is one primitive operation. Returning from a method is a primitive operation. Evaluating an expression, so this could be addition, this could be evaluating if an expression is true or false. These are examples of primitive operations. Now, the exact definition of it isn't super important. We're going to see why soon enough. But the idea is we just want to count how many primitive operations an algorithm incurs in the worst case. That way we can use this as a method of showing how efficient it is. And the reason why the exact definition isn't important is because we're going to make this even a little bit easier for ourselves later. We'll see that in a moment. So let's see an example first. So let's go back to our array max algorithm, what we had, and count up how many primitive operations there are. So we have, let's see here. Right here, we've got two primitive operations. One is coming from, we're accessing the 0th, the first element in this index, and we're also assigning a variable. So those are our two primitive operations. Now in our for loop, we actually have a lot of things going on here, so I tried to break this up to make it clear where those primitive operations are coming from. So inside the for loop, what's hidden here is that we actually have a lot of things going on here. We have one operation is that we're assigning the value of 1 to the variable I. Our second operation is evaluating the expression n minus 1. And we have another n operations where we're checking to see, in order to continue through this for loop, whether this value I is still less than or equal to this value. Okay? So we have one operation here is coming from the variable assignment, one operation is coming from evaluating the expression n minus 1, and then n operations where we check to see is I less than or equal to that value that we n minus 1. Now also what's embedded inside that for loop, and I kind of moved that down here so we can count it separately, is once we're finished executing these lines, then we also increment the counter I. That's one primitive operation, evaluating what is I plus 1. And then a second primitive operation there is assigning that new value to the variable I. And we do this n minus 1 times because that's how many times we go through this for loop. So that's just separated a little bit there. Okay, now inside our for loop, which we know we're going to execute the for loop n minus 1 times. So let's see on this line, we know we'll execute it n minus 1 times, but we also have two primitive operations which occur there. So one is in accessing the ith element of this array, or at index I of this array. And our second primitive operation is then evaluating the expression, is that element in the array greater than current max? Now, if this is true, we'll proceed on to the next line. Now, don't forget, we're evaluating the worst case runtime. So in the worst case, we would go through this if statement every single time. So let's evaluate, if that happened, still how many operations are we executing? So again, in the worst case, we'll execute this line n minus 1 times. This is how I got the n minus 1 here. and then how many primitive operations are on just a single line. One is accessing index I of our array, and our second one is assigning this value to the variable current max. So we have 2 times n minus 1 primitive operations. Okay, and then the last thing we do outside of our for loop is we return that variable current max, which is one primitive operation. So if you add all of these primitive operations up together, you get 7n minus 1. So our array max algorithm takes 7n minus 1 primitive operations in the worst case. So this is a function of the input size n, how many elements we had. So we can use this in order to estimate the running time of an algorithm. So we know that array max requires 7n minus 1 primitive operations in the worst case. And remember that primitive operations include a few different basic operations like accessing into an array, assigning a variable, evaluating an expression, etc. And some of those basic operations may be a bit faster or slower than the other ones. So for example, maybe accessing into an array, maybe this is the fastest primitive operation and this takes only 0.0001 seconds. Whereas, addition, that might be a slower operation which takes 0.00002 seconds. But no matter what the fastest or the slowest primitive operation is, we know that the running time of our algorithm, of array max, so T of n is the worst case running time of array max. We know that this is bounded by a function of 7n minus 1. So 7n minus 1 was how many primitive operations it required in the worst case. And if all of those primitive operations were the slowest primitive operation, we know that the worst case running time can't be any more than whatever the slowest primitive operation was times however many primitive operations we had. But we also know that in the worst case that the amount of time that this will take is at least whatever our fastest primitive operation was, however long that takes, times however many primitive operations we had. So this function, 7n minus 1, gives an upper and a lower bound up to some small constant, a or b, of the worst case running time. So this is a good expression of the worst case running time of our algorithm. So this actually describes the growth rate of our running time, because this is a function of n. So estimating the running time this way lets us evaluate algorithms independently from the hardware and software. Changing the hardware or software environment will change T of n only by a constant factor. That's the A and B, slowest and fastest primitive operation. So if you have a really fast computer, the amount of time that takes will be faster, but it doesn't change the growth rate of T of n. So that our running time of array max required 7n minus 1 primitive operations means that it has a linear growth rate. It depends only on n, and that's an intrinsic property of our algorithm. So we're going to look at growth rates of algorithms. So there's a few common ones that we'll see. And remember, this growth rate, this isn't affected by constant factors or lower order terms. For example, we had that array max took 7n minus 1 primitive operations, but we still refer to this as a linear function. So this is what I meant earlier when I said the exact definition of a primitive operation isn't super important, because if you counted in the previous slide, you ended up getting, maybe you counted differently and you still got 7n plus 2 or 5n plus 3 primitive operations instead of 7n minus 1. All of those, still n is the dominant term there. That's the highest order term, which means that for each of those functions, those are all linear functions. So we'll describe the running time of an algorithm as constant, logarithmic, linear, quadratic, cubic, polynomial, exponential. There's a few others too, but just to see how those growth rates compare. So here I have a graph charting, here's how much time, or you can think of this as how many primitive operations an algorithm requires as a function of the input size n, how many elements our input. So here we have a constant function. This means that it doesn't matter what n is, we're still going to have the same number of primitive operations. It doesn't depend on n at all, in fact. This is ideal. If we have a constant function, this is great. It doesn't matter how large our input is, it will always run in constant time. And the next, just of what I have here, the next fastest one would be a logarithmic function, followed by a linear function. That's what our array max was. A quadratic function, so this is n squared. A cubic function, so now this is n to the third power. And then kind of any polynomial you can plug in here. So for example, n to the fourth power would plot right here. N to the fifth power would be, a little bit slower in the sense that its growth rate would be faster. And then exponential function would be here. So this is some constant number a. So maybe this is 2 to the nth power or 3 to the nth power, etc. So you'll notice I have a kind of colored background here, just in terms of how ideal this growth rate is. So definitely our goal is to have the most efficient algorithm as possible, which means we want our growth rate to be small, to be slow. If the growth rate is slow, such as a logarithmic or a linear function, then that means even for a very large input, because the growth rate is slow, then the running time would be really quick, even for large input. So a slower growth rate means a faster running time. So ideally, we would like to have something within this range, something which is constant, logarithmic, or linear. And then if that's not possible, and there certainly are problems where it is impossible to create an algorithm which runs in that amount of time, then we can kind of work our way up this list. And unfortunately, there are even some problems where we can't do any better than exponential. So we'll see an example of that later. But the goal of this is we want to be able to describe, say we have a running time, an algorithm which requires this many primitive operations, 10 squared n plus 10 to the fifth power. We're just going to describe this as, this is a linear function. Or in the second case, because n squared is the dominant term here, we can describe this as a quadratic function. We'll see how this is formalized with asymptotic complexity in the next video. So at this point, try taking the short quiz Q1.1 on primitive functions and growth rates. And as always, if you have any questions, please post them on Piazza so that either myself or another student can get back to you. Usually, I could see your faces right now to know if I should go through another example or slow down or speed up, but at least you can rewind the video if you missed something. And again, please, if you have a question, the odds are that someone else also has the same question, so please don't hesitate to post on Piazza. And remember that you can post anonymously to other students if you would prefer. So I will see you in the next video.